This is another example of using the geometric distribution. If you look in your S1 textbook at page 116, there's an example 7.3.1 in there, which I'm going to go through. It says a darts player must start each game by hitting a certain section of the dartboard. The probability that any single dart hits this section is 2/5. The player keeps throwing darts until he hits the required section. Calculate the probability that he needs, in part A, exactly 5 throws. So before we look any further, we've got here success is hitting the dartboard. So X will be the attempt where he hits for the first time. The attempt which hits for the first time. We've got a constant probability of success here, 2/5. We're going to assume that it's independent. What happens on one throw doesn't influence another throw. We've got success and failure, hitting and not hitting. So X will follow the geometric distribution because he's going to keep going until it happens for the first time. And then in a bracket we put our P value. So our P value here will be 2/5. So in part A, it asked what's the probability he'll need exactly 5 throws to get his first hit. So we want the probability X equals 5. And the formula we had for the probability for geometric distributions was 1 minus P to the R minus 1 times by P. That's failure every time except the final one where there's a success. So for this question, the probability that X equals 5 is 1 minus our 2/5 to the power of 5 minus 1 times by our 2/5. So that's 3/5 to the power of 4 times by 2/5. And if you work that out, you get 0.0518. Part B of the question is saying, what is the probability he will need at least 8 throws? At least 8 throws means X is going to be 8 or more. We can include 8. At least 8 throws is 8 or more. So what we have got here is the scenario we saw before. It's one of these infinite sum things. For greater than or equal to 8, what we have got here is, well, it could have been on throw 8. It could have been on throw 9. It could have been on throw 10. And so on. And that can carry on and on and on. So what we're going to do, we're going to look at each of these and try and work out what the first term is and then what that ratio is. So first of all, probability is on the 8th go he gets his first hit is going to be failure 7 times and then a success. Probability X is 9, his first hit is on the 9th throw, it's going to be failure 8 times and then success. And the probability his first success is on the 10th throw is going to be failing 9 times and then success. And if you look at the pattern here, ask yourself, what are you multiplying by to get from one of these lines to the next? This bit is staying the same. You're multiplying by an extra 3/5. Here there were 7 3/5 times together. Here there are 8 3/5 times together. Here there are 9 3/5 times together. So you're multiplying by 3/5 each time. So that is your R value for your ratio in the formula we need to use. That value there for your first one in the pattern, that is what we're going to call A. And we had before that what we need is a sum to infinity, which is A over 1 minus R. So if we put our values in, A is everything up here in this box. 3/5 to the power of 7 times by 2/5. And on the bottom it's going to be 1 minus R, which is 3/5. And what happened before, your spot happens here again. 1 minus 3/5 is 2/5. So there's 2/5 on the bottom of the fraction and there's a 2/5 up here as well. They will cancel out and you are left with 3/5 to the power of 7. And if you work through out 3/5 to the power of 7, you will get the answer 0.0280. The next part of the question, part C in this question, is saying what's the probability he needs at most 10 throws. At most 10 throws means up to and including 10, but no more. So that's the same as the probability x is less than or equal to 10. So what we could do here is we could add up the probability he's successful in his first throw, the probability he's successful in his second throw, his third throw, his fourth throw, and so on, all the way up to his 10th throw. But that's a lot of work. And whilst it sounds strange, it's actually easier, rather than add up 10 sums, to add up an infinite number of sums. So think about what is the exact opposite of less than or equal to 10. The exact opposite of less than or equal to 10 is greater than 10. So the probability of x is less than or equal to 10 is the same as 1 minus, because it's the opposite, x is greater than 10. In other words, 1 minus the probability that x is 11, I'm going to put a bigger bracket in there, or x is 12, or x is 13, and so on, all the way up to infinity. And this is a sum to infinity thing, which we can actually add up very easily. X is 11. What's the probability of that? Well, it means we fail 10 times, and then we have our success. X is 12 means we would fail 11 times, and then have our success. X is 13 is we would fail 12 times, and then have our success. And we will be adding all of those up. I've still got this 1 minus that's going on here as well. And this is this thing that we call an infinite geometric progression, an infinite GP, where we can add that up. We use this notation S with a little infinity sign, as A over 1 minus R. Remember, A is the first term in the pattern. So A is that. That is A. And R is what you multiply this by to get that one. Well, that is 3/5. R is going to be 3/5. That is what is having the increasing power on it each time. So everything that's over here on the right is just equal to A, which is this bracket here, over 1 minus R. I've still got this 1 minus out the front. Just like before, that 2/5 there cancels with that 2/5 there. So I'll get my answer by working out 1 take away 3/5 to the power of 10. And if you work that out, you'll get an answer of 0.994. There are other parts to this example, and you'll find those in the next video.